for this for those who can't make it. So there's a classmate actually who have notified me, who has notified me that she won't be able to make it today. Okay, now this time we'll be considering reactions that are said to be varying in volume in the course of the reaction. So for varying volume reaction, there must be a, shall I say, a formula that we will relate to the final volume with the initial volume. In that formula later on, you'll be see that there's a new characteristic parameter. Okay. Now, this varying volume bus reactor primarily is used in the microprocessing field, where a capillary tube with a movable bead would represent the reactor. Or comparable to later on, you will compare this particular reactor to a tubular reactor or a plug flow reactor. Then this is also used for isothermal constant pressure operations for reactions with single stoichiometry. So take note here the term single stoichiometry, meaning there's no need for you, or the problem will not require you anymore to, let's say, prove a particular rate equation that is provided together with a set of reactions. At this time, the reaction, the chemical reaction or the stoichiometric equation is already provided for you. And that particular stoichiometric equation or your chemical equation is already representative of the entire thing that is being talked about in the problem. So single stoichiometry. So we will not be talking about mechanisms of reaction here. I have already mentioned this thing that it's isothermal and isobaric constant pressure. Now, let me see again if you, I think I need not project this because everything cannot be shown if I will project it. I don't know why. So I mentioned a while ago that there should be an equation that will relate original volume or initial volume to final volume. And this particular equation has this characteristic parameter which I called as the epsilon A. This epsilon A is the fractional change in the volume between 100% conversion. You see here XA equal to 1 to 0% conversion, or from 0% conversion to 100% conversion. Epsilon A is to be solved using the formula that you are to substitute here the volume when there is 100% conversion for A minus the volume when A is not yet converted over the volume when A is not yet converted. This too, the volume when A is not yet converted is actually your initial volume V sub O. Whereas this V is your final volume when A is assumed to be 100% converted. Now, in the formula here that you see on top, you have initial volume being multiplied to 1 plus epsilon A XA. So you have now the epsilon A here. And aside from that, since this is a constant, by the way, just like VO is a constant, so now the relationship that you're seeing here is actually between conversion and the final volume of your system. How is the final volume of your system dependent on the degree of the conversion of your reactant A? Now, from this same formula, I will not anymore show the derivation. You'll be able to get XA, the degree of conversion, derived from this particular expression, and it would be equal to V minus VO over VO epsilon A. So this one just came from this formula. So there's no need for you to memorize this one as long as you memorize this. So there's a need for you to memorize. If I think it's this one is in your handbook, so there's no need to memorize also, okay? If you know where to find it in your handbook. If you will differentiate this derived formula for XA in terms of V, you will be having this particular equation on the right. So dXA is equal to dV over VO epsilon A, knowing that the derivative of an initial volume, which is a constant, is 0. So one formula, this one, and this. Because this one is different, it's not dependent on this one, whereas this two is dependent on the main formula relating the linear relationship between V and conversion. Okay, so now we will proceed. Now, from that formula that was shown to you, let me check if I can have everything projected here. So I cannot. So I will have to not project, not put it on slideshow. So based on the formula that was shown to you, you will have now this rate expression, RA being equal to negative dCA dt. And this one, this time your CA here class was converted to this. Your CA here in the dCA, the differential of CA, when converted to this expression, will yield a new representation for the dCA dt, the negative dCA dt that you have here originally for constant volume reaction. So this is now your rate expression in terms of conversion. Now, XA also from this particular formula, so by the way, class, this is one formula. This is one formula for varying volume batch reactor. And you have this added formula. The third one, this one just came from this. Okay, so your CA being equal to this times CAO times the quantity 1 minus XA all over the quantity 1 plus epsilon A XA. So if you notice, this one is the original CA when volume is constant. But if volume is not constant, you have added this expression in the denominator. This XA just came from here. Okay, so if you know this formula, the conversion can be solved out of this formula. So you have now 3 formulas. Now from what you have here on top, you can have another expression for dCA dt, this time in terms of changes in the volume. And since we're talking about a varying volume reaction, then we expect that the volume will be changing. So now you have an alternative formula for negative dCA dt in terms of changes in the volume. So this negative dCA dt will be now CaO dV over V times epsilon A dt. Now this dV over V we know is ln V. So that's the derivative of ln V is actually dV over V. So this one was just taken, or rather this one was just taken from the dV over V that you have here. So these two are just equivalents of each other. So aside from this representation of negative dCA dt, in terms of conversion, you have an alternative formula in terms of changes in the volume. So CaO dV over V epsilon A dt. Okay? If you're going to ask me, you have actually 5 new formulas to take note of in varying volume batch reactor. You have 1, this is 2, this is 3, this is 4, and this is 5. So 5 for now. Now good, since in here in gaseous reaction, you are most of the time given the order of the reaction, or it is stated already in the problem what is the volume of the reaction. So in that case, your integral analysis will be pure substitution excuse me, to the formula that are already pre-derived for you. So let's go to integral analysis. So just like constant volume batch reactor, this is also divided into 2 categories. The topic that is, one is for integral analysis and another one is for differential analysis. Although it's very seldom that we use differential analysis for varying volume batch reactor, most of the time integral analysis will do. Okay, because the data that is provided is not really that big, about that integral analysis will not be applicable. So we go to zero order irreversible reaction, specifically varying volume reaction, but zero order. Now the formula for that would be this, CaO over epsilon A ln of V over VO. So notice this time that you are now accounting for the changes in the volume and you are to determine epsilon A. So there will be corresponding examples later for you how to determine epsilon A in 2 different scenarios. Okay, now this is for zero order irreversible reaction. If it's a first order irreversible reaction, this will be your formula. Then in here, you again accounted for the changes in the volume. So your delta V will be final V minus V sub O, initial V. And again, you have the epsilon A in here. First order irreversible. If it's second order irreversible, we only have the two cases here. We don't have the third case wherein we're dealing with a second order irreversible reaction but non-elementary in nature. So if you recall in the first part, we have three cases under second order and third order reactions. The third case in both cases are all pertaining to non-elementary reactions. In here, we will not be talking anymore to second order irreversible reactions, non-elementary in the case of varying volume reactions, or those reactions that are isobaric, isothermal. Now, the two cases that would be applicable here is when you have a single species, but you have bimolecular, so you have a coefficient here of 2. And the other one is when you have two species, but you need 1 mole for each, so still bimolecular. Now, in this case, it's important that you understand, class, that for this second scenario, your initial concentration for A and B has to be equal. What does this mean? That even if your stoichiometric equation, this one, is A plus B, but the initial concentration of A and B are not equal, then it will not have the same working equation as what is provided here. So this will only work for this particular scenario, complete with all the conditions stated. So A plus B, all having 1 mole, reacting with one another, and initial concentrations have to be equal. In the two cases here, this is your working equation. Second order irreversible varying volume reaction. So this is for the integral analysis. So we only limit uh, to zero first order and second order irreversible reactions. We're not even talking about multiple reactions in the case of gaseous reactions. Now, then that leaves us with the last part, which is the differential method of analysis. And I am explaining it here just like the way it's explained in our main reference book. So the differential method of analysis for varying volume data will be very simple, similar to that of shall I say, integral method of analysis for constant volume data. But this time, instead of having the slope of that particular chosen point that you have plotted against time in your best fit curve, in the constant volume batch reactor data, the slope is dCA dt. In this case now, the slope is not dCA dt, but it could be this one. CAO dV over V epsilon A dt. Actually, this one is just equivalent to this. So your slope now is not dCA dt in the case of this particular type of reactions, varying volume, but rather this one. So what you're going to plot is actually the ln of V versus T. And then the corresponding slope will be this one for a differential analysis. And that is for varying volume reactions. Now, I will limit our applications to this particular topic on varying volume reactions to, if you're going to ask me, to integral analysis, because anyhow, what is important is you know how to interpret large bulk of data using differential analysis for constant volume reactions. So we will only limit it to this case. Cases. It could be that for a particular reaction, for example, in the first case, it's carried out at constant volume, then that particular reaction now, which you know already, the rate law could be, I say, processed in a variable volume reaction. It could be like that. But as long as we limit it to this scenario. So no multiple reactions, limited only to these types of reactions. zero, first order, and second order. So it's already complex as it is. So if you're going to include here multiple reactions, that will make even things more complicated. Anyhow, based on the undergrad requirement in the CMO, what's to be covered on the topic of varying volume reaction, this would suffice, because based on PRC requirement, Levenspiel is the book that is to be used for chemical reaction engineering. And we're using that book. And we're not leaving any topic in that book not discussed, except for very few wherein the interpretation are more inclined on graphical approaches. But 95 to 98% of everything that is written in Levenspiel, we are covering. Okay, so in terms of examples on this, we will go to our book and check what we can work out in terms of problems where we can apply the formula. Okay, I have here actually the part where I read. You have the soft copy of Levenspiel here. I'm showing it to you. And this is what's written there. So this is how short he discussed differential method of analysis for varying volume reactions, meaning that there was not much emphasis on the use of differential analysis for gaseous reactions. So we go to and the formulas that I gave you are the ones that are also written in here. Then it talks about the determination of the activation energy and all. A short discussion on that. Miss, ang PPT Japon ang na-share. Sorry. Okay, I will share the book. Sorry. We have chemical. Okay, do you see the book already? I'll go back to where what I was talking a while ago. You see the book? This is the book that I have been mentioning. Let me see. Okay. So this is the explanation in Levenspiel based on differential method of analysis. So there was not much focus on that, telling us that we'd rather use, the author is even suggesting that we use integral analysis for that matter in processing problems concerning varying volume data, batch reactor data. Now, these are the formulas that I have placed on the slides for you to use. And that's it. That's how short it is. Then it goes to temperature and reaction rates based on Arrhenius. So Arrhenius was discussed last in here. Okay, then now you have the problems. Okay, so we will now look for, there are final notes, by the way, here. It would help you if you're going to read it. It talks on a summary of the different things that were discussed by the author in that entire chapter. Very short though. It will not take much of your time, because if you're going to combine everything, it will just be a single page. So we look for a problem. I think I have already used it previously, but I forgo the solution because it's varying volume. Okay, I think here we are. Oh, 3.29, Levenspiel. Find the first order rate constant for the disappearance of A and the gas reaction 2 moles of A forming R if, on holding the pressure constant, the volume of the reaction mixture starting with 80% A decreases by 20% in 3 minutes. Okay, and you could read on the, by the way, the problem is just a single statement. Single statement. Find the first order rate constant of the disappearance of A in the, says here, gaseous reaction. That in itself will tell you that you are not to assume that this is constant volume, because it's gaseous. And then 2A forming R. If on holding the pressure constant, so another one here, pressure is constant. So the volume of the reaction mixture starting with 80% A decreases by 20% in 3 minutes. So you have gaseous reaction and pressure constant throughout the process, telling you that this is not a constant volume reaction. So this is varying volume, and there's a need for you to determine the fractional change in the volume, which is the epsilon A. Okay, I took a picture that way. We will not have to go back to that. So let's go to the solution to this problem. So this is 3.29 from Levin's field. The statement already says that it's a first order rate constant that is being required. Determine or find the first order rate constant. So that tells you you have to be keen that the order of the reaction is 1. A is the disappearing according to this reaction, stoichiometric equation, and pressure is constant. So both temperature and pressure is kept constant, and this is a gaseous reaction. So it says here that the volume starting with 80% A decreases by 20% in 3 minutes. So our V, the final V, if there's a corresponding decrease in the volume by 20%, then our final V will just be 80% of the initial V because there's a decrease of 20%. So this is for the time it took to the decrease in volume took 3 minutes of reaction time. Now, it is to be noted, however, that there is this phrase, the volume of the reaction mixture starting with 80% A. So, you did not start with 100% A, but rather you have some inerts present in your A in this particular reaction here. So A here is not 100% pure. So we will have to start with starting with 80% A. It follows that the other 20% would be inerts. So you are starting with 80% A with 20% inerts for this particular reaction. Now, there's a big difference, class, if the problem is starting with pure A than with unpure A, or if there are some inerts present in your reacting species. That will be illustrated by the next sample problem. It is easier if the reaction is using pure species, no inerts present, because it's easier to determine in that case your epsilon A. But if it's not starting with 100% of the reacting species, just like this one, you have to consider that one. Okay, now whenever you see a gas reaction and whenever you see a statement at constant pressure, so that you won't forget, always start with epsilon A. You always write down epsilon A, meaning there's a need for you to determine epsilon A. So that is the volume between 0% conversion to 100% conversion. Okay, now this volume at 0% conversion of A, I have already explained it a while ago. This one is equivalent to the initial volume. This initial volume need not really be specified by the problem. Okay, so we then know for this time now, we know this too. By the way, class, this is 0. Okay, so we know this and we know this. Between 0% conversion to 100% conversion. So this should be XA equal to 0, not 1. So we know this, that leaves us with volume at 100% conversion. Now, this for now temporarily will be set to equation 1 because we do not know yet the other volume. The volume at 100% conversion, of course, will take into account the volume of the inerts. Okay, because you have inerts, this particular inert volume will still be the same volume even if you have already 100% of your species being converted. So you have volume of the inerts plus this time volume of the, if I may ask, if your A is already 100% converted, then you will have to account for the final volume as the volume of the inerts plus the volume of the what in this case. Since A is already fully converted, so that the final volume will be the sum of the volume of inerts, which remains unconverted, and the what? Anyone? And the, correct, Joe Byrne. So it would be
Volumes
the,
of product, Miss.
that would be the volume of the R. So that would be now the volume of the R. I'll place there volume of R because it's already converted. It's already produced from the conversion of 100% A, of your A. In this case, it's not 100% A. Now, the volume of the inerts, we know already that we started with 80% A. So the volume of the inerts would be 0.20 V sub O. Since we only have 80% A, then 20% of the initial volume is that for the inerts. Next is the B sub R. So then we have a problem with this. So our problem is determining the B sub R. So question mark, what is B sub R? Okay, so now we will set this as equation 2. So we will have another slide for the V sub R. For your V sub R, you are going to rely on what you have in the stoichiometry. So since we don't have volumes provided, or rather we initially in our discussion with kinetics of homogeneous reaction, we did not discuss how we make use of the stoichiometric equation in finding for volume. Now is the right time to introduce this. So we're looking for the volume, not RO, but rather the volume of R. So we can use the stoichiometric equation in finding the volume of your reacting mixture due to the formation of R. The volume of your reaction mixture due to the formation of R. Then we can use the stoichiometric relationship that we have. From the stoichiometric equation, we know that the amount of A consumed divided by 2 will be equivalent to the amount of R produced divided by 1. This 2 and 1 came from the reaction, the chemical reaction. Then, if you will substitute for this one volume of A, so you can write here 0.80% V sub O, 0.80% V sub O because we did not start with 100% A divided by 2, and we have, this would be now your V sub R divided by 1. So your V sub R is equal to 0.4 V sub O. Now you can substitute this to equation 2. So in your equation 2, you have V at 100% conversion. So you have V at 100% conversion of A is equal to the inerts plus the volume due to the formation of R, 0.4. So in this case, you have 0.6 V sub O. Now, since you already have 0.6 V sub O, you go back here to the first equation and substitute. So your substitution will yield epsilon A being equal. So this is your 0.6 VO. And by the way, what we have there is 0.2 plus 0.4, that would be 0.6, and that should be placed in here. So you have 0.6 VO minus VO all over VO. So in this case, you have a negative 0.4 V sub O over V sub O. Now, it would, you may find it, why is this negative? Is this not acceptable? By the way, your epsilon A can be negative, it can be a whole number, it could be a fraction. So we now cancel the V sub O, and your epsilon A is equal to negative 0.4. Now, when you know already epsilon A's value, it's so easy because all you have to do is recall the formula for, in this case, we're provided that our reaction order is 1. So you go back to the formula for a first order reaction. So you have negative ln of 1 minus delta V all over epsilon A V sub O equal to KT. This is the one that we're looking for, the rate constant for a first order reaction. Now, in this formula, you have the delta V. So what is the delta V? So your delta V would be, so you are after the change in the volume. So you have a decrease in the volume by 20%. So I wrote a while ago that V is 0.8 VO. So you write 0.8 VO minus VO. Then your delta V will be negative 0.2 V sub O. You can go back here and substitute all the information that you already determined. So your delta V is negative 0.2 V sub O divided by the epsilon, which is negative 0.4. And you have V sub O. You have K. And the time given is 3 minutes for the volume to decrease by 20%. So we cancel the V sub O. This gives you a rate constant, which is 0.2310. So this is per minute because our unit for time is in minute. So this is your rate constant for this first order varying volume batch reactor. Okay? Batch reaction rather, not the reactor, because your reaction is facilitated only in the reactor, but this K is a characteristic of your reaction, not your reactor. So this is your rate constant. So far, any questions? So this example illustrated to you the manner of determining the epsilon based on the identity of your species, whether it's starting with 100% of that species or have some inerts present. Okay? The rest as to determination of the final volume and all is just a case of properly understanding the information provided and use of algebra. No question?
Yes, Miss. Hello,
Yes.
Miss.
Sige.
Si Joshua, Miss. Miss, maas ko pala, Miss, sa slide before ni Miss. Sa slide before ni Miss.
Slide, yeah, sa PowerPoint.
Or, hindi, Miss. Ang sa next ni Miss nga solution.
Sorry. Okay. Ini?
Para pala, Miss, ang Miss, nag-equate ang CaOXA sa 0.8 VO, Miss. Gin-equate na sila, Miss, or Miss nga, Miss, nag-miss na 0.8 VO na siya.
The relationship that we have for concentration here, the amount of A that has reacted was compared to the amount of A in terms of volume. Remember that the problem said that you have started with 80% A. 80% A, meaning of the entire initial volume, you only have 80% A. And this particular amount Di ba? This particular amount will be all fully converted to R. So then this would also represent the amount of A that will be used up in forming the R. So this is what I said a while ago, that even though in the kinetics of homogeneous reaction, it was not covered that you can use volume in lieu of concentration. In this case, you can still, because in terms of analogy and principle, you're not violating anything. Remember, this one represents the amount of A that was converted. And in here, we are determining the volume due to the formation of R when everything of A was converted to the formation of R. And what is this everything of A? That's 80% of your initial volume, because the problem said that you only started with 80% A. Did you get it, Josh?
Okay, miss. Thank you, miss.
Okay.
Analogy sa galing sabi ko.
Ah, pero
Thank
ano
you.
siya, miski analogy lang siya, pero 'di ba correct man sa scientifically kiti ini siya ho amount of A ni siya mo. Although this has the unit of mole per liter. But this one has a unit of volume. But in terms of concept and principle, do tsakto man lang kay ti ini siya amo ni i-convert mo pakadto kay R. Galing kay we don't have the unit of mole per liter here. We have the unit of volume. But nonetheless, these two just represent the same thing. The amount of A initially present, which was all fully converted to R.
Okay, miss. Thank you.
Okay, okay. Some more question? Okay. So if there's no more question here, we'll go to the next problem. We go back to the problems we have. Okay. Here. This one is simpler than the first. Okay, why is this simpler? Then let me read the problem. So find the first order rate constant for the disappearance of A in the gas reaction A forming 1.6 moles of R if the volume of the reaction mixture starting with pure A increases by 50% in 4 minutes. In the previous problem, there's a decrease. In here, there's an increase by 50%. The total pressure within the system stays constant. So take note again. So the term, the pressure staying constant and it's a gaseous reaction dictates that you will determine the epsilon A. So it's a constant at 1.2 atm and the temperature is at 25 degrees Celsius. So we will write down the solution to this problem here. Let's go back to our board. So we start off with the given. It's asking for the first order rate constant. So then you have a first order reaction. Now your stoichiometric equation is unlike the other stoichiometric equation provided to you, because this time you see a coefficient that is not a whole number. It's okay. In here, it's okay because sometimes the equations that are provided are hypothetical in nature, not like in chemistry that we are dictated that all the coefficients of the species in our reaction should be all whole number. So if you recall your chemistry before, kinahanglan mangita ka gid sang number nga i-multiply mo sa bilog nga imo nga chemical reaction para ang tanan nga coefficients mag whole number. Dire, you need not do that. So your stoichiometric equation is A forming 1.6 moles of R. Now, the problem also stated that the final volume is 50% more because there's an increase in the volume. So that would be 1.5 V sub O. And it took that thing to increase by that much in 4 minutes. Now, it's constant pressure, 1.2 atm, constant temperature, 25 degrees C. So telling us that there's a need for us to determine epsilon A. Okay, so you still need the K. And before you forget anything, write right away epsilon A. That way you will not forget that there's a need for you to determine it. Now, by the way, you might be having a question. Is there a scenario wherein my epsilon A will be a zero? If your epsilon A will be a zero, then let it be a zero. Anyway, as long as you are not, should I say, you are doing everything correctly, then if it's a zero, then it is a zero. What happens if epsilon A is equal to zero? Based on the formula that I have presented to you, what happens if epsilon A is equal to zero? This is out of the problem already, just crossed my mind. What happens if epsilon A is equal to zero? Anyone? Basi magrato ka mo lang nga nag-zero ni. Di ba dapat may value ni? Kay variable volume ni ayhan.
Wala reaction, miss.
Wala
Hello.
reaction? Bo grabe
Equal
man.
ang volume yun ko. Ay, equal ang gabon ang volume.
Sino to lang ba wala reaction? Marcel, Mr.
Joke lang, miss.
President, sino to?
Bali, miss, same lang ang volume. Bala, miss, ako. Nga,
Ay, salamat. Ging correct mo. Hindi nga wala sang reaction, kundi the volume, initial and final will just be equal. Remember our formula? So I'll go back to the slide so you will recall. Whenever you are asked something like that, you go back to an equation that you can use. That way, you are sure that you will not make a wrong statement. So you see this one? If the epsilon A that you have computed, the reaction, the problem says it's gaseous and it's constant pressure, then of course, it's emphasized that you start solving for epsilon A. What happens is, if when you solve for epsilon A, your answer is zero. Oh, is zero. Hala, sadya. Bali, misali, may epsilon A giniya. May epsilon A gani. Pero kung naso mo siya nga zero, doesn't mean nga sa lain mo answer. Because if your epsilon A is zero in here, then it tells you that even if the reaction is gaseous in nature, even if it's carried out at constant pressure, the volume must keep constant as well. So it tells you here that VO is just equal to B. So hindi mang problema nga nag-zero ni siya. Base karon hindi ka na mag-solve dayon kay zero siya sa lain mo answer. No, it's not that. It's just like that. And it could happen also. Not that when you're given gaseous reaction, you are expected to really have an epsilon A value. There are cases, class, wherein epsilon A is also equal to zero. So don't rattle na it should not be equal to zero. So in this case, I said it's simpler. That is why I asked that particular question. Anyway, this is a very short problem. When your problem is silent about your species, original species having inerts, the problem is very, very easy to solve. You don't need to have the ratio of the amounts reacted or converted to 100% of the product in the case of sample problem number 1, but directly you can make use of the stoichiometric coefficients that are found in your chemical equation or your chemical reaction. What do you mean, miss? Directly use the coefficient of the product for volume at 100% conversion and directly use the coefficient of the reactant, minus 1 over 1. So in your case here, you will have an epsilon A which is equal to 0.6. Now, question, miss, what if I have several products here and I have several reactants here? What will you do in determining the epsilon A? You will add. You will add all the coefficients of your products, and that would be the number that will be reflected here for volume at 100% coefficient, 100% conversion. And the volume at 0% conversion or initially is the coefficient of your reacting species. Or if you have several, you just add them. Okay? Okay, that's your epsilon A here. And this one is very easy to solve. So you have to do is use again the formula that we used a while ago. So you have negative ln of 1 minus 0.5 V sub O over 0.6 V sub O equal to K times the time, which is 4. Now, where did you get this? This is your V minus V sub O. Your V is 1.5 V sub O minus V sub O, telling you that your delta V is 0.5 V sub O. So this is your delta V actually. Final volume minus initial volume. So you get to cancel this, and your K here will be equal to 0.44794 again per minute. Okay? What if the reaction that is provided to you is not first order? It's second order, it's zero order. The same procedure applies in determining the epsilon A. The only difference is the formula that you will use in determining whatever the problem is requiring from you. It could be the K or it could be anything that the problem is requiring from you. Okay, but the process in principle on how to determine the epsilon A will be exactly the same. I think Levenspiel only provided us with two problems on this particular topic, varying volume batch reactor, wherein you are provided with volumes, initial and final for the said reaction. So this would be the appropriate sample problems to use. So we will have a 5-minute break after here. We'll use the next link because I'll be giving you your seat work for the next hour, because actually we're done with interpretation of batch reactor data. We're done with midterm. So what will happen on Wednesday, you will have your quiz, but for your, shall I say, for your something like a review for your exam next week, I'll be giving you a problem set that will more or less be reviewing you for what is expected on the exam next week. Okay, so we'll end for now here temporarily. I'll stop sharing now. And